Welcome back, students, and hello, students. And yes, welcome back to our next part in this topic of elements and compounds. And as you recall, yesterday we began learning about the language of chemistry. And I introduced to you the symbols are like the alphabet. Hopefully, you took my advice and you started learning the names and the symbols of some of the common elements yesterday. You're going to need that today and in the future. And how those symbols can come together in order to form what we refer to as formulas. And yesterday we went over and finished up with chemical formulas, the shorthand for chemical substances, and kind of use the analogy that chemical formulas are like the words in the language of chemistry. And I want you to refresh your memory here with this illustration from your notes and how this chemical formula is made up of symbols and subscripts. And hopefully you remember what those symbols and subscripts refer to. And I showed you the little model here yesterday of water made up of 2 hydrogen and 1 oxygen atoms. That is the formula or the recipe for water. Because we're going to build on this knowledge here today as we move forward into creating sentences or chemical equations. Chemical equations is where it's all at in chemistry. Chemical equations are a shorthand for chemical reactions. And the most exciting part, in my opinion, about chemistry is chemical reactions. Some of them are more exciting than others, and I'm hoping that we'll have opportunity to explore some of the more exciting chemical reactions. But here we go. Here is an example of a chemical equation. Now, you may recognize some of this here. You may recognize the H2O. H2O is the formula for water. And I mentioned to you we're going to find out exactly how to make water. Well, here it is, step-by-step instructions on how to make water. It requires this element here, symbolized by an H, and that element is hydrogen, added to this element here with the symbol O, which is oxygen. So when you add hydrogen and oxygen together, they can form H2O, which is water. Now, here's the deal. In chemistry, and I want you to think about maybe a baking analogy for a moment. Do any of you like to bake? Do any of you like to bake cookies or cake? If you ever need a guinea pig to taste your baking cookies or cake, you let me know and I'll be there because I've got a sweet tooth for baking. I love cookies and cake of pretty much any kind. Now, if you have ever baked something from scratch, well, you know there are certain ingredients that you need. You need, let's say eggs and water and oil and salt and baking powder, baking soda. Did I say flour? Don't forget the chocolate chips or peanut butter or whatever else it is that you're putting in. But whatever those ingredients are, if you've ever baked, you undoubtedly know that the directions or the recipe for making something has certain quantities or amounts of those ingredients. Now, think about it. If you were making chocolate chip cookies, but you didn't have any chocolate chips, when you finished baking your cookies, yeah, they might taste yummy, but are they going to be chocolate chip cookies? Of course not, because there are no chocolate chips in them. Likewise, If your ingredients call for, let's say, a cup of sugar, and instead of sugar, you added a cup of salt. They look the same, right? They kind of look similar in a measuring cup. But if you bake those cookies, are you going to want to eat them? I don't even think an animal would want to eat them if you use a cup of salt instead of a cup of sugar. My point is this: when cooking or baking, there are recipes to follow with certain quantities of certain items, certain ingredients. It is the same way with chemistry. And over the next few weeks, we're going to learn more about this. But for the time being, if we look at this chemical equation, you'll see these other funky numbers here. Now, we know what the little numbers are. The little 2, the little 2, the little 2, those are called subscripts, and they tell you the number of atoms. Just look up in your notes. But what about these big numbers in front of things here, in front of these symbols, in front of these pure substances? In fact, hydrogen is an example of a pure substance. It's an element. Oxygen is an example of a pure substance. It's an element. Water, H2O, is an example of a pure substance. It's a compound. So what is that number 2? What is that number 2? What are these big number 2s in front of these pure substances called? That's a very good question, and it deserves a good answer. They are called coefficients. A coefficient also tells you some very important information. Without knowing the coefficient, if you tried to use this chemical equation as a recipe for making water, you could be in for a rude awakening. Because as we know, H2O is water. But if you don't have the right proportion of hydrogen and oxygen and don't combine them in the right way, then you might result in H2O2, which is rocket fuel, hydrogen peroxide. We don't want to end up with that if we want to make water. So you've got to know, again, the overall language rules here in chemistry, starting with coefficients. So coefficient tells you the number of molecules there are of a substance. So yesterday I showed you a model of water, and it looks like this. Here is a model of water, and more particularly, this is a model of one molecule of water. But you'll notice in this equation that there is a coefficient of 2 in front of that molecule of water. And what that coefficient of 2 is telling us is that if we follow this recipe, this chemical equation for making water, we're going to get 2 molecules of water. Now, again, that may not seem like a big deal to you yet, but when we get into balancing equations later on, this is going to be very not only useful, but critically important information. So that, I just broke water. Right on my laptop. Oh my goodness, let me clean it off here. Oh golly, okay. Thankfully, it didn't make a mess. All right, so we'll get back to those models a little bit later on, but I want you to understand the difference between subscripts and coefficients. Subscripts, think of the name itself, subscript. Think of a submarine. Sub means below the surface. So the subscript here is smaller and written below the surface of the symbols. The coefficients, co means with or cooperating. The coefficient is the same size as symbols. They are cooperating. They are together. the same size, and they tell you the number of molecules of a particular compound or substance here. Now, what about this arrow symbol? Well, the arrow symbol is read as the word yields. Unlike a math equation where you have an equal sign, in a chemistry equation, you have a yield symbol. The arrow indicates the direction of the chemical reaction. This particular equation is showing us how to build water from hydrogen and oxygen. But if this arrow were in the opposite direction, it would show the chemical equation for chemically separating water into hydrogen and oxygen. And guess what? Both things can be done, and both things we will do at one point in the laboratory. We're going to build water and we're going to tear it down. And this is probably one of the simplest equations that we can see and understand because we're so familiar with water. And we've heard of hydrogen and oxygen. But we're going to play around with some other chemical equations as well. Now, as you look at this chemical equation, it has other parts that I need to instruct you on as well. We are already now familiar with the names of, with the idea or the concept of symbols, formulas, subscripts, coefficients, but a chemical equation itself has different parts to it. Just like a sentence has a subject and a verb, and you need both of those in order to create a complete thought. Likewise, chemical equations have different parts that are essential for the full, complete understanding of what's going on in an equation. So let's start with the yields symbol. The yield symbol, that arrow, divides or separates the chemical equation into two basic parts. The parts to the left of the yield symbol are referred to as the reactants. And make sure you're getting this into your notes. The reactants are the substances that react with one another. And boy, isn't that kind of a simple way of referring to it. Sometimes scientists just find very easy ways of referring to things. So reactants refer to the substances that react with one another. Substances that react are called the reactants. Over on the other side of the chemical equation are the substances that are produced. And those substances that are produced are called the products. So take a moment and look at this chemical equation, because no matter what the symbols and formulas might be, and I've given you a couple different ones here, and in a moment I'll ask you about them, but you may not know what this is a chemical equation illustrating, but even if you don't know the symbols, you should be able to identify the parts of the equation and distinguish between the reactants and the products. So let me quiz you a little bit here. Here's a new chemical equation, and we have a couple new symbols. Capital F, lowercase e. Yell it out if you know what that is the symbol for. Iron. That is what Fe is. Now, some of you might be thinking, wait a minute. Oxygen is O. It begins with an O. I get that. Hydrogen, H. Hydrogen begins with an H. I get that. Iron begins with an I. Why is the symbol Fe? What's up with that? You may be asking. Well, I'll tell you what's up with that. Different elements were discovered at different points in history. Iron was one of the earlier elements that were discovered, identified, and named. And we haven't always used English in the history of the world. And so science used to use a lot of Greek words, and the Greek word for iron is ferros. Ferros. Ferros begins with an F-E. That's why iron symbol is Fe. Now, in your book, I have given you a page which we will be exploring in the future, but I'm just going to make reference to it now because some of you might be interested in learning more about this. But in the next unit, topic number 13, we're going to spend a whole week on the periodic table. And I've included a couple pages in your book. First of all, on page 119, I've given you a periodic table. And in fact, that's a good page to refer to even this week's topic to know where it is. But on pages 122 and 123 is a list of all of the elements and some really cool information about each of those elements, including when it was discovered and why the symbol is what it is. So I would encourage you to turn to topic 13 at the end of the lesson today and just look over that list and maybe familiarize yourself with the reason why some of the symbols may not be as obvious to you at first glance. Because remember, you should still be studying some of those common elements and their symbols for this week's topic. They will be on this week's quiz. Hint, hint. So make sure you're doing that. So hopefully you've got that. If not, watch it again. But chemical equations, no matter what the symbols are made up of reactants and products, and they are separated by the yields symbol. Now, there's one more symbol there, capital letter S. Yell it out if you know what the symbol capital S stands for. It is sulfur. Sulfur is S. So this is actually a chemical equation for combining iron and sulfur into a very dramatic, through a dramatic reaction, which looks like bubbling lava and spewing yellow smoke and sparks out of a test tube to create iron sulfide. We will not be performing this lab. In the past, I've had too many complaints about this lab activity that I make the school smell like rotten eggs. So I may refer you to a video of this particular equation. It is pretty cool, but we won't be doing this one in the lab. All right, enough about chemical equations for the time being. We're going to be coming back to them, believe me. Right now, I want to spend the remaining bulk of our time talking about how we write chemical formulas. In other words, how do we arrange those letters into words? How do we arrange the symbols into formulas? We're going to be using lots of formulas for the remainder of the year, and you're going to be writing them yourself. So you need to know some ground rules. First, whenever we have a compound, it's made up of two or more elements, as you know. And in a compound, when writing a formula for a compound, the symbol or the letter for the metal is always written first. Well, that's all fine and good if you know what a metal is, right? Well, as we will discover, many of the compounds, not all, but many of the compounds we're going to be utilizing this year at least, are made up of at least one metal and one non-metal. So the first symbol that will be written will be that of the metal. Well, all right, how do we know which one is a metal? Well, I'll tell you this. When looking at a periodic table, and you now know where one exists in your book, page 119, there's also one in the appendix in the back of your book, if that's easier for you to find. And there's also one in the science lab. You can look at the wall at any time because that is a tool. You don't have to memorize the periodic table unless you're learning the periodic table song. There's hydrogen and helium, and I won't sing it for you right now. But where are the metals? How do we use this tool of the periodic table to find metals? They are on the left side of the periodic table. The left side of the periodic table. More specifically, periodic tables are separated with what many chemists refer to as a staircase. The staircase is typically a boulder line on many periodic tables. You'll see it in your book as well. But this line here, the staircase, separates the metals from the elements that are not metals. The orange ones here are referred to as metalloids, and we'll get into that a lot more when we get into the periodic table in a couple of weeks, and the nonmetals. For the time being, just know that the metals are on the left of the periodic table. And if you look at the periodic table, you may be able to find some symbols of common elements that are familiar to you as metals. For instance, Fe, there's iron, Ni, nickel, Cu, copper, Zn, zinc, Ag, silver, and below that, Au, let go my gold. Au is gold. We know that these are metals. And which side of the staircase are they on? The left side, all right? All of these elements here are metals. You may be familiar with some, not familiar with many others, but that's okay. They're all metals. So when writing a formula, again, you start with the symbol for the metal, which is found on the left-hand side of the periodic table. Next, we write the symbol for the non-metal. The non-metal is second. And so how do we know where the non-metals are? They're on the right-hand side of the periodic table. So again, they are divided by that boulder line, that staircase. So the elements to the right of the staircase, those in the yellow zone here, you can say, these, over here, these are the non-metals. And if you think of just finding some common ones that you do know, like O for oxygen, oxygen's not a metal. I'm sure you already know N for nitrogen. Nitrogen's not a metal. And now you know S for sulfur. Sulfur is not a metal. These are not metals over on the right-hand side of the periodic table. So we start with metal first always and non-metal second when writing a chemical formula. Now, here's another thing to include, and this is a general rule. It isn't always the case, but in general, at least the compounds that we will be writing, the non-metal the name will end in IDE. So when we name a chemical compound and we're writing the formula, we usually start with the name of the nonmetal, followed by the name of the metal, followed by the name of the nonmetal, ending in IDE. Hopefully this will become clear to you as I give you an example. For instance, sodium chloride. Here's the name of a common compound. You know it from yesterday by its more common name of salt. Table salt is chemically known as sodium chloride. Now, I want you to think about that for a moment. What is the symbol for sodium? Pause the video if you need to hunt for it now. Now, I'm going to ask you, what is the symbol for Chlorine. Chlorine is the element. Chloride is how you end the word when writing or reading a formula. So find the symbol for chlorine right now. All right, so hopefully you now know the symbols for sodium and chlorine. So the compound sodium chloride, if you write the metal first, followed by the nonmetal, you can tell me what the chemical formula is for sodium chloride. Write it down first, and then look at the screen. Write it down. Is that what you got? NaCl. NaCl is the chemical formula for sodium chloride. So if you got that, great job. Now, this can be done in reverse as well. For instance, if I gave you the chemical formula, NaCl, you would be able to identify the names of those two symbols and then write the words down, sodium for Na, chlorine for Cl, but take off the last words and add IDE to turn it into chloride. You could have named that chemical compound. All right, so let me give you another one here. Iron oxide. Iron oxide. Take a moment, find the symbols for iron and oxygen, and see if you can write the correct chemical formula for iron oxide. Pause me if you need to. All right, is this what you got? Did you get FeO? FeO? You probably got FeO, but some of you might be saying, yeah, I got FeO, but why do you have a 2 written there? Huh? What's up with that? We'll get to that later, okay? But if you wrote FeO for now, great job. But I'll be getting into those subscripts later on because we have to build up a little bit more information. Now, by now, you've probably recognized on the periodic table that there's more information on the periodic table than just the symbol and the name. I'm going to introduce this to you now, but again, when we get to the periodic table, we're going to discover the usefulness of this information a lot more. But there are 118 squares called element squares. And these element squares have very useful information. Usually at the top can be found the atomic number, whatever that is, the symbol, that's like the 1 or 2 letters representing the element, by whose name you recognize, usually written under the symbol. And finally, on the bottom of the square, it is the atomic mass. Don't worry about the atomic number or the atomic mass now. We're just taking our time through our study of chemistry, and right now we just need to know the symbol and the name. So on the periodic table, you've got that. So if I were to show you a series of chemical equations here, I don't want you to freak out by all of the symbols and the numbers. If you can simply identify the letters are symbols, the numbers down below are subscripts, and the numbers in the front are coefficients, that's great for now. By the way, these are some of the reactions that we're going to be performing in the laboratory tomorrow. So stay tuned for some excitement in the lab tomorrow. But for now, I'm going to end our video for now, but I'm going to add 1 or 2 video clips into Google Classroom that you can feel free to watch, including Minecraft Explains. You can check out the link to this video as Minecraft explains this whole topic of elements, compounds, atoms, and molecules. And some of you, if you're into Minecraft, will find this very helpful to you. So until tomorrow, when we perform our lab activity, I am going to simply say bye bye.